In previous video, we saw convolution theorem, convolution definition, and first property, that is change of scale property. In this video of Fourier transform, mathematical physics 2 MSc second semester, another property that is known as shifting property. If you have f of s is a Fourier transform of f of x, either you call it complex Fourier transform, or you can say generally Fourier transform. Basically it's a complex Fourier transform, but generally we can say Fourier transform. Then Fourier transform of f of x minus a, because here f of x means x is going to shift by some amount a, x minus a. The Fourier transform of this form of function is basically nothing but exponential iota s of a f of s, means f of s means Fourier transform of f of x. This can be also written in this manner: exponential iota s a Fourier transform of f of x. For finding this result, we know that the Fourier transform of any function f of x is f of s, that can be represented in the form of minus infinite to plus infinite f of x iota sx dx. Therefore, the Fourier transform of f of x minus a can be represented in the same manner, minus infinite to plus infinite. At the place of f of x, we can write f of x minus a exponential iota sx dx. Okay. Then put x minus a is equal to t. This portion you are going to put t. So therefore, if you differentiate this dx, it's a constant, zero differentiation, dx is equal to dt. Limits are what? If you change the variable, then limits are going to change. So limits are basically, if you put minus infinite here, then minus infinite. If you put x is equal to plus infinite, then plus infinite. So therefore, Fourier transform of f x minus a is equal to nothing but minus infinite to plus infinite in t. Exponential iota is this, s is this, x is replaced from here. X is equal to what? If you are going to take minus a in this side, so you will get the t plus a. T plus a is here. Then x minus a is basically f of t, because this replacement, and dt is basically dx is equal to dt. Then from here again same thing, exponential iota x t and exponential iota s a. From here you will get this result. So one of this is constant totally, isa with respect to t. So then isa is the constant, iota sa is constant. Then you can take it out the integral. So minus infinite to plus infinite, exponential iota st inside f of t dt. This is basically again a representation of Fourier transform. Same thing is here, same thing is here, only change are in variables. Here f of x, here f of t, here iota sx, here iota st, here dx is dt. Though if you change the variable, replace the t with x, then you will get the same thing. This is basically f of s, then put here. So this is the required result. This is the required expression. Okay, now next, if you try to find out this result, Fourier transform of exponential iota ax f of x is equal to Fourier transform of Fourier transform of exponential iota ax f of x is equal to f of s plus a. Now, if you are going to multiply f of x with exponential iota ax, then you will get this result. So for finding this expression, we are trying to write, we will from left side, if you write the Fourier transform of left side, Fourier transform of this portion, then it can be write in this form by the definition of Fourier transform. So Fourier transform definition is basically minus infinite to plus infinite. Function is here, so this is the function total, and exponential iota sx. Okay, this is the function, these two are the function, and exponential iota sx dx. So here these two are the common, exponential iota sx and exponential iota ax. So these two powers can be added with the property of addition, exponential iota s plus a x f of x dx. So as you see, this result again a representation of Fourier transform. Only change is here, the s is going to replace s plus a. Okay, so this is again for f of s plus a, Fourier transform of f of x. The Fourier transform of f of x is f s plus a. Okay, hence proved. Next property, if Fourier transform of f of x is f of s, then Fourier transform of f of x times x raised to power n is minus iota raised to power n differentiation n times dn over dsn f of s. Now for finding this result, again we know for f of s is the Fourier transform of Fourier transform of f of x minus infinite to plus infinite, exponential iota sx f of x dx. So as you see here, d of n dsn is basically differentiation of this one. So for finding this result, the results so as you know here the differentiation, so if we differentiate this with respect to s, then we will get this differentiation. So first we are going to differentiate this equation. Let us suppose this equation is 1. Differentiate the equation 1 is with respect to s both sides. So next page, we will get differentiation of f of x with respect to ds. Df of s over ds is equal to minus infinite to plus infinite. Here differentiation goes inside the integral. So integral is basically with respect to x and differentiation is basically with respect to s. So d over ds is goes here and differentiate only s functions. So here s is here. So if we differentiate e raised to exponential iota sx, then again you will get the same result, exponential iota sx, and other remaining things you will get here iota x This is the differentiation in right side. Again differentiate with respect to s both sides. Then d2 f of s ds square minus infinite to plus infinite iota x square now, because from here the differentiation of this portion with respect to s will get iota x exponential iota sx. So iota, it means iota sx is same, and the iota x one more, then it will be square. So f of x dx. Similarly, if you differentiate 3 times, 2, 4 times and n times, so generally here ds differentiates dn over dsn f of s is equal to minus infinite to plus infinite, and iota x raised to power n exponential iota sx f of x dx. Then from here iota raised to power n is come out, minus infinite to plus infinite x raised to power n f of x exponential iota sx dx. This is again a Fourier transform representation. So this is the Fourier transform of x raised to power n f of x. Check it with standard formula of Fourier transform. So dn fs over ds raised to power n iota raised to power n, this is. So our purpose only find out this portion. So this portion is here and this portion goes to down. So here is this, and again this is same. Here we are trying to take it above I, then multiply I raised to power n upper and lower part, and you will get this. And I raised to power n is here, I raised to power 2n is here, I raised to power I square raised to power n means I square is minus 1 raised to power n. Then this is same, dn over dfsn, nothing change. So I minus 1 is here, minus 1 goes up to minus I raised to power n, because power of minus 1 and I raised to power n is same, then common power. Then this is final result. This is a proof. Hence through f of x raised to power n f of x is minus I raised to power n dn f of s over dsn. Now fifth property is f of Fourier transform of differential function f prime x is nothing but this is basically f prime x is dfx over dx is equal to minus iota s fs if fx tends to 0, as x tends to plus minus infinity. For finding this, we know that this is the Fourier transform definition. Therefore Fourier transform of f prime x is nothing but minus infinite to plus infinite exponential iota sx is same is here, f of x is f of prime x dx, where this is this. Then next phase, Fourier transform mathematical physics 2 MSc second semester. Fourier transform of f prime x is equal to minus infinite to plus infinite exponential sx df of x over dx. Basically f of prime x is represented in this form dx. Now integrate by part RHS this side. Consider this one is the first function, this one is the second function. So the rule of by part is basically first function exponential iota sx, integral of second function differentiation of f of x over dx times dx. Limits are minus infinite to plus infinite, then minus infinite to plus infinite differentiation of first function integral of second function dx or whole integration dx. uh, exponential iota sx. Integral of this portion is basically this is going to cancel, dx cancel, only df of x is here. Limits are same, minus iota sx. If you differentiate this portion, so exponential iota sx, exponential iota sx is here, differentiation, and then iota x. Okay, this portion differentiation is iota x, iota s. Iota s is goes out. Integral, this portion is cancelled, dx to x cancel, df of x, integral dx. Okay, now here exponential iota sx, exponential iota sx, integral df of x is f of x, minus infinite to plus infinite, and minus iota s, minus infinite to plus infinite, exponential iota sx, f of x, integral of this portion is f of x dx. So as you consider here, means here f of x tends to 0 as x tends to plus minus infinite. So see here, if you put the limit here, f of x plus infinite or f of x minus infinite, then you will get the 0, because this thing and this thing, f of x is tends to 0 as x tends to plus minus infinite. So same is here. If you put the limits, exponential f of plus infinite is 0, f of minus infinite then 0, then this portion is totally 0, only this portion is left, minus iota s, f of s. This is basically a Fourier transform representation. So this is represented here. So you will get the result, required result. Okay, now next numericals, some numericals. One numerical, this is the numerical Fourier, find Fourier transform of f of x function 1 upon epsilon mod of x is less than equal to epsilon 0 mod of x is less than greater than equal to epsilon. Okay, this question your university exam question, PU exam 2018 May, in 2018 this question was asked in your exam, in MSc exam. So solution of this question is basically, and one more part of this question is, hence determine the limit. What happened if limit is going epsilon is tends to 0, then what happened on this Fourier transform of the result of Fourier transform of this function. Solution, we know that the Fourier transform of f of x is f of s minus infinite to plus infinite, f of x exponential iota sx dx. Fourier transform of f of x is equal to minus infinite to plus infinite, f of x we can break minus infinite to plus infinite domain in subdomains. One, we can move minus infinite to minus infinite, f of x exponential iota sx dx, plus then minus infinite to plus infinite, f of x exponential iota sx dx, then plus infinite to plus infinite, plus epsilon to plus infinite, sorry, 1 minus infinite to plus minus epsilon f of x exponential this, and then minus epsilon to plus epsilon f of x exponential this, and then plus epsilon to plus infinite f of x exponential this. Okay, the nature of function is defined. F of x is equal to 1 upon epsilon mod of x is less than equal to epsilon means this can be written in this form: minus epsilon is less than x is less than plus epsilon. Mod of x is greater than epsilon means x is less than minus epsilon and x is greater than plus epsilon. So the sketch of this function basically is this is the sketch of this function. The function is in this range is 1 upon epsilon, in this range is 0, in this range is 0. So this is the sketch of given function. Here is 0, here is 0, or here is the range, this range here. Then this integral is 0 due to this range, because here function is 0, this is 0, here function is 0, this is 0, because this is the greater than epsilon portion, this is the less than epsilon portion. Only this portion is function f of x is 1 upon epsilon. So put it here 1 upon epsilon, here 1 upon epsilon minus epsilon plus epsilon exponential iota sx dx. Integral of this portion is this, all of you know, and minus epsilon plus epsilon limit. If you put the limit, then you will get this. Multiply both sides to upper and numerator and denominator by 2. So this is basically this. So f of x is equal to f of x, Fourier transform of f of x is equal to 2. This is basically nothing but sine of epsilon s. This is epsilon s. This is the answer. And what happened if limit epsilon tends to infinite? Fourier transform of f of x is equal to limit epsilon tends to 0 to epsilon to sine epsilon s upon epsilon s. So here if you are if epsilon limit goes to 0, then this portion epsilon tends to epsilon s can be written as epsilon s only. So epsilon s, then epsilon s is going to cancel with epsilon s, and answer is 2. So you can easily determine the limit of this portion. Now next question, we are going to look about the next question of Fourier sine transform and cosine transform. Fourier before 15th of March, Fourier series complete, and Fourier transform of some portion is complete. Some questions also complete before the 15th of March. The next question is Fourier sine and cosine transform. Sine transform complete, Fourier sine and cosine transform. Now we are going to look about the sine and cosine transform. So question is basically find out the Fourier sine transform and cosine transform of exponential x raised to power n minus 1 and second 1 by under root x. So for Fourier transform, as I told you before the 15 March, the formula about the Fourier transform and Fourier sine transform. So Fourier transform can be represented as Fourier sine f of x is equal to under root 2 upon pi 0 to infinite f of x sine sx dx. In some books, under root 2 upon pi not available, because in some books Fourier sine transform and Fourier sine inverse transform, under root 2 upon pi with Fourier sine transform and under root 2 upon pi with Fourier sine inverse transform. In some book Fourier sine transform is directly 0 to infinite f of x sine sx dx, okay, and Fourier sine inverse transform 1 by 2 upon pi, just 2 upon pi, not under root 2 upon pi, just 2 upon pi 0 to infinite f of s sine sx ds. So only this is not a problem, okay. Either you can take the under root 2 upon pi, either you do without under root 2 upon pi. Only the answer results are going to change, because under root 2 upon pi is here, then results are different, and under root 2 upon pi is not there, then results are different. But method of integrating 0 to infinite f of x sin sx dx does not change. Okay. So this is the basically f of c, means Fourier transform, cosine transform of f of x under root 2 upon pi, under root 2 upon pi 0 to infinite f of x cos sx dx. Okay, so put the value of f of x here. F Fourier sine transform x raised to power n minus 1 under root 2 upon pi 0 to infinite x raised to power n minus 1 sin sx dx 1, f of c x raised to power n under root 2 upon pi 0 to infinite x raised to power n minus 1 cos of x sx dx is equation 2. Put the value of f of x in these two formula. Multiplying equation 1 y iota and adding to equation 2. So you will get f of c, means cosine x raised to power n minus 1, this portion, and iota is here, then this add, and under root 2 upon pi is common in both cases, and limits integrals of both equations are same, so you can take it common, 0 to infinite. So cos x sx plus iota is here, sin sx, x raised to power n minus 1 is common, and dx. So this can be written in this form, under root 2 upon pi 0 to infinite exponential iota sx x raised to power n minus 1 dx. Okay. On putting iota sx is equal to minus t, because why we are going to put minus t, because we are trying to convert this formula in the gamma function. So I sx dx is equal to minus dt. Limits are, if x is 0 then t is 0, if x is infinite then t is infinite. Okay, so put here f of c x raised to power n minus 1 iota f of s x raised to power n minus 1, this is this under root 2 upon pi 0 to infinite exponential minus t. Okay, and exponential minus t, because this term we consider minus t, and x from here, x is basically minus t by is, so here minus t by is x raised to power, so this raised to power n minus 1, and dx is basically this minus dt over is. Okay, then next sheet. Sheet number 4. Okay, then this is the left side, this is right side, under root 2 upon pi, and from here from here exponential minus t, from here minus 1 raised to power n minus 1, from here minus 1 raised to power 1, so 1 is minus raised to power plus 1 and 1 is n minus 1, then result minus 1 raised to power n only, minus 1 is going to cancel with plus 1. Okay, and here or iota s raised to power n minus 1 in denominator, and iota s plus 1 is denominator here, so minus 1 or plus 1 going to cancel, then you will get here iota raised to power iota s raised to power n. So these two things are goes out because independent of t. 0 to infinite e raised to power minus t. Here here t raised to power n minus 1, t raised to power n minus 1, and then dt. Okay, this is nothing but this is basically formula of gamma n. So this result is can be represented as gamma representation. This is the gamma representation, gamma n. So under root 2 upon pi minus 1 can be represented as my iota square raised to power n. Here iota raised to power n, s raised to power n. So iota raised to power 2n upside and iota raised to power n downside. Then you will get the resultant iota raised to power n, 2n minus n, n. S raised to power n, gamma n. Okay, under root 2 upon pi, this I can be represented as iota can be represented as cos pi by 2 plus iota sin pi by 2. Cos pi by 2 is 0, iota sin pi by 2 is 1, then iota. Then this iota can be represented in this form, gamma n. Okay. So Fourier transform of cosine transform x raised to power n plus iota Fourier sine transform x to n minus 1, x raised to power n minus 1, x raised to power n minus 1 is equal to under root 2 upon pi. This result is this, and this is same is here, s raised to power n is here, equating both sides, real or and imaginary part. Okay, the real part is this here, real part of this here, so real part is this, and imaginary part is this here, the imaginary part is this here, then you will get this. If you put for second situation, second basically this problem of finding the 1 upon under root x, and here we can take one more, that is third, 1 by x suppose. So putting n is equal to 1 by 2, so here if you put n is equal to 1 by 2, here you will get the minus 1 by 2, because 1 by 2 minus 1 by 2, f cosine transform of 1 by under root x is equal to f of c, x raised to power minus 1 by 2 is basically this, under root 2 upon pi, under root, sorry, this is not under root, this is the gamma 1 by 2, or under root this is basically 1 by 2, if you put here 1 by 2, then you will get under root s. So under root s, not gamma. So cos pi by 4, if you put here the cos pi by 4, all of you know cos pi by 4 is basically 1 by under root 2, then you will put the all values, then you will get the 1 by under root s. Similarly, if you put here x n raised to power 1 by 2, so you will get the again 1 by under root s. So cosine transform of 1 by under root x, sine transform of 1 by under root x are same, 1 by under root s. Okay, so this is basically important result. This is basically important exam point of view as CSIR net. You are going to remember every time this result for CSIR net purpose, yeah, gate purpose. So always remember this result. So directly you can, if in CSIR objective type question, so they ask about the Fourier cosine transform 1 under root x, 1 upon under root x, so you will get the 1 by under root s. So now if you put the n is equal to 0 in above result, then Fourier cosine transform of 1 by x is 1 by under root 2, all things under root gamma 0 is 1, basically s raised to power 0, this is under root 2 upon pi, and Fourier sine transform of 1 by x, if you put here n 0, the under root, then under root 2 upon pi, under root 0, and s raised to power 0, and sine 0 is 0, basically 0. So thank you. This is all about the Fourier transform, okay, and Fourier sine transform and Fourier cosine transform. Okay, in your exam, no more than such material, this material can be asked. And thank you. in next video we will learn about the Laplace transform. After the Laplace transform, your second unit complete. Okay, thank you.